you very much. Yes, this is joint work, as you can see there, with Liam Newcomb of the British Computer Society and also David Wallam of the Oxford University Research Centre. And we're talking about carbon and cost accounting based on per service model. So this talk's in three parts, and perhaps the most important one is this section of why we need per service accounting. Then we're going to note a little bit on why implementing it is hard, and then we've got some ideas for a particular solution. And perhaps we're saying in the context of today, what we're looking at is measuring software and processes running on top of hardware, perhaps in a data center, perhaps in a supercomputer center, perhaps in distributed organizations. And so we're instead looking at things above the level of hardware and so forth. So we're not looking at just how efficient any individual piece of hardware is. And we're trying to relate the cost of running this software, cost of using this IT, to achieving effects. So the sort of effects, whether it's monitoring climate change or whether it's increasing GDP, the sort of thing that's been talked about earlier in the day. So a lot of work's been done on improving the energy efficiency of data centers, and there's a whole set of things up there which we could go into lots of detail about, but we won't, because that's not the topic of this talk nor today. We've heard all sorts of things today of other ways of increasing energy efficiency of IT, and all of these things are absolutely great, and I'm not knocking them at all, but I do want to note two problems. First problem is a massive increase in demand for IT. It's not going to go away, and frankly I think if we don't address this question of demand, some of the nice graphs that people have shown are going to turn earlier in the day, they're really going to turn out to be a bit optimistic. For example, I quote here, just 2 weeks ago, when I was at the Open Grid Forum conference in Barcelona, a representative of a platform told me that his customers are planning for a 50 times increase in processing power in 3 years. Now, Moore's Law will give you, I think, a factor of 4 over that time, and you might say, okay, they'll do a bit of virtualization, or they'll improve more advanced chips and so forth. But there's no getting away that if their customers want 50 times processing power, and they're customers who can pay for it, we're talking about big engineering companies or financial companies, they can install that much processing power. That is going to increase the carbon usage of their organizations. And you've seen similar things here. You've got the EU Code of Conduct that Paolo introduced earlier has got various figures and so forth. And all the energy-saving technologies that we introduce, great though they are, win only once. The demand doesn't go away. And of course, it's been remarked earlier, if you make IT more energy efficient, you make it cheaper, you unlock demand, and therefore you get more people trying to use more of it. So I think if we build this stuff and we make it available more or less for free, people will use it. The other problem is how do you measure efficiency? Now, at some levels, when you're talking at very low levels, or talking about a particular set-top box or whatever, you can do that. But if you're talking about a platform for providing software, it's much harder. It depends on what problems you're running. It depends on the size of the input data. It depends on where the stuff is run. So when people have been looking at measuring efficiency of data centers, they've tried to come out with things like, well, how many spec-ins is this processing power, or what transactions per second if you're looking in a business thing. Well, that depends, of course, on what the value is of the software you're running, what the business effort is you're trying to achieve. And you can't bring that question of varying workload down onto a single figure for an entire data center. So we contend that the answer is energy accounting per service, or per task, because this macro scale restriction or targeting of IT energy use just isn't going to give you an accurate measure of what you want. And in particular, I mean, as technical people, and the three of us writing this board are primarily technical people, we can look at improving the IT efficiency of individual bits of kit and putting them together in clever ways and hopefully producing better results. But we don't know what the business value is of any service that's run. It's not a decision the technical people in the company should be making, it's a decision that the business people should be making. So what we should be asking is, as it says here, what is the marginal environmental or economic benefit of this IT system? So if you're running an IT system to improve, to look at mitigating climate change, you have to balance how much is gained versus the cost of running the system. And at the moment, you don't have a way of measuring the cost of running the system. So that's what we're trying to look at. So the advantages of doing this, well, for one thing, it enables energy optimization of business processes as well as IT. Outside a few tech-oriented folk, basically all IT is run to support a business process. And you can make the IT efficient. That doesn't, of its own, make the business process more efficient. For example, do people really need to run the job on the IT? So some engineering simulation tasks, they run this sort of whole spread of processes. And if one of them breaks, they think, oh, well, I'll just resubmit everything. Now, maybe they could just resubmit the one. There's all sorts of cases where you can do continued optimization, and maybe there's a break-even point. And that's not even being asked. Because typically, I mean, to be honest, I mean, most people who run data centers don't see the energy bill, and it certainly isn't passed up to the people who are running the processes. It supports business planning. You know, if you've got a CO2 allocation through cap and trade or whatever, you say, well, how am I best going to use the CO2 allocation I've got? I've got all these different things I want to do. Which one of them, or which set of them, are the ones I want to do? At the moment, there's no way of answering that question. And it does introduce some demand management into the system, so that if we techies build it, can the business guys actually afford the CO2 to run it, and so forth. So maybe it will help reduce this demand curve as well. So that's the argument for why we need per-service accounting, and that's really the main take-home message. The next take-home message is that implementing it in modern IT infrastructure can be quite challenging. And this is because we've moved away from the old method of where we'd have a single machine dedicated to a task, sitting somewhere in a room and lots of things looking after it. We now have, we realized that that was getting utilization rates of maybe 7% of a server. It's a complete waste of all the energy that goes into building a server. It's the complete waste of the energy going into powering it and into powering the power supply units and the cooling and everything else. So most people now are moving towards virtual machines. You may have tasks being moved from one machine to another depending on workload. And you may have tasks actually split across different machines and so forth. And then which brings in communication. You've got the network load between them. Even if you had a single dedicated machine, you've got the question of measuring how much carbon, how much energy is used varying on the workload. And that problem is still there. But it's compounded by the fact that we're now using processing as a commodity and moving tasks around to where it's most efficient. I could go into that a lot more, but I think this basically sort of gives the gist of the argument. So, I've got 5 minutes, I'm on time. How do you deal with this? So, there's a number of ways, but the way we're approaching it is looking at coming up with a detailed model of a data center based on simulation. This takes the IT workload, it takes a detailed map of the server load to a power function, and then maps that onto the whole power of the data center itself, including all the things like uninterruptible power supplies and all the cooling and everything else. So first of all, you need a model of how your data center works. So if you run something somewhere on a machine, what's involved there? Next proposal, within a data center, you typically have a lot of kit that's basically the same, repeated. Not across the whole data center, but across various subsets of it. So we're assuming you've got a grid infrastructure linked up to this data simulation, and we're assuming you've got a grid scheduler that's sending jobs to the different places in the data center. And that's beginning to be fitted now into the commercial virtualization technology as well as into the more research-oriented grid stuff. And it's been there in some of the database grid things for a while. So, assume a modular infrastructure of subgrids, each internally homogeneous. That's the assumption. So in each subgrid, we say you install detailed metering for a small set of the server nodes. So you don't meter everything everywhere. That would be incredibly expensive, and you'd then have to take into account, well, how much carbon and energy is going into creating the metering and running the metering and all that sort of thing. So you'd just do a small set of typical server nodes in each subgrid. You define a detailed simulation of energy usage in the data center using the BCS model that I presented on the previous slide. Then for each application you're going to run, you characterize its energy usage on the metered node. So you do a pre-production run of typical workloads, characterizing what the energy use is. This, we believe, will then let you run in production on the whole grid. You track where and when each task or request is executed. You have a scheduler that's moving things around, so you know where things are run. You know the power characteristics of the machines you're running it on. You know the characteristics of the task you're scheduling. So it's not a simple piece of work, but you can use all this to map, to account for how much carbon and how much energy you're using. So you then charge the user based on a function of these characteristics of the running applications and the overall power drawn. So you do run this in a sort of checking mode. You do check the overall power and make sure that the figures you're coming up with are reasonable compared to what's actually being used. So you're calibrating it as you run it, but you're not doing detailed power metering. So that's the proposal, and we've got a project that's looking in implementing this and testing it and seeing it doesn't got the right approaches. A little bit on characterizing workloads. I explained this was quite difficult, and it is, but we aim to do this using 4 key values. So for any task, and it's in task data that gets sent to run on a processor, it induces a load on the processor, and of course then access to main memory, so we have main memory I/O as well, and disk I/O, which may be SAN or maybe local disk or whatever, and also network I/O from one node to another or across the system. Those 4 values are already being used in some work to characterize workload, and now you just have to parameterize those on the task data, because your workload will vary depending on the different types. As your task runs on different data, your workload will vary to some extent. So that's the aim. The key point of this is that the scheduler, the grid scheduler, or the VM scheduler, whatever, actively allocates workload to nodes. Therefore, it can collect data of which tasks execute where. And you use this building on the workload characterizations you got. The workload characterizations have to be approximations, but the hypothesis is that they're accurate enough to predict usage for purposes of cost allocation. Okay, and as I said, when you're running this in production mode, you have a calibration system there. So you divide the cost of actual power among the workloads based on the approximations you've got. And then you have some warning if predicting actual power diverge significantly, because clearly you then have to do some more work and look into what's going on. So obviously this has to be tested, this all has to be built and evaluated and so forth to see does this approach work. But that's the aim of the work we're doing at the moment. So the take-home message, and as I say, the first point is the key one. We believe you need per-service accounting. We think it's essential to enable informed business decisions, and that can be business in the sense of increasing your own profit of the company, or assessing on how effective it is to attack a particular problem, such as modelling climate change or whatever. The implementation is hard, but grid and simulation may be a solution. And these are my colleagues. Liam is in the audience here at the back, and I don't think David made it down from Oxford today, but there are also some URLs there where you can go and look for more information. So Grid Computing Now is the knowledge transfer network that I work for. The DCSG is the data centre specialist group of the British Computer Society, and the Low Carbon ICT is a project being run at Oxford University looking at improving their own use of energy within Oxford University. Okay, thank you very much.